All right, so welcome everyone to participate in the monthly development cycle from CleanRL. In this development cycle, we're working on batch constrained Q-learning. So this week I haven't had much chance to play around with it, but Rosalind had quite a bit of update of tuning BCQ to work with D4RL sort of style offline benchmark. So I guess, Rosalind, if you like, feel free to take over the presentation and just sort of maybe go over some of your findings.
Okay, just setting up the content. 1 or 2 minutes. What was the paper's name again?
Let me see. Batch constrained. Even if you just search batch constrained, it'll show up.
Technically, it's called off-policy deep reinforcement learning without exploration. But yeah, I just search for batch constrained Q learning and it comes up.
Yeah,
I think actually quite a few batch constrained work.
Oh, really? I usually just search for BCQ RL, BCQ space RL, and usually the author's implementation of BCQ is what pops up first.
Okay, from the GitHub, I think I can access the paper, probably.
Yeah, nice.
Okay, got it. Well, as a disclaimer, I only did a really simplified implementation of the algorithm.
Yeah.
Okay, where is the screen sharing also?
Sounds good.
Could you please share the link to the WebGB reports with everyone?
Yeah. Would you like to maybe share screen?
Yes, I'm going to share the screen, but okay. It should be working. Good.
Yep. Got it.
I think the most important point would be the algorithm here. You can basically just follow this, manage to make it somehow. So, I don't know if I should jump directly straight to the code.
Do however you want.
First, since we are most familiar with techniques like DDPG and SSE, I think most of the hyperparameter and the structure of the code does not actually change it. Actually, I use the SAC CQL as a base for this one. So, the Q function, the policy evaluation process, sample from the dataset, also the dataset does not change. So what really changes here, I would say, is the maximum perturbation hyperparameter. The sampled action, this is the thing that I actually ignore first, but I will come back to it later. And then the minimum weighting, which our memories of SAC CQL are still fresh, correspond to the mean Q term weighting, like alpha prime, I believe they call it.
Okay.
Which decides how conservative SAC CQL is. Then, on top of that, we have the VAE, which is probably the most challenging implementation part. And on top of the VAE, the perturbation network. So, without further ado, I guess, quickly jump to the implementation of the VAE first. So, as I said before, the structure of the code is mostly the same. In Slack.
Got it.
The dataset loading over here. So far, no much change. The Q network also declared here. And then the VAE policy. So as inputs, we have the observation chip on the states. action and the latent. I think as there here. So the first component is the encoder, like EW1 here, which takes the state and the action and tries to compress it into the latent variable Z here to somehow capture the distribution of the state action distribution of the expert in the data policy, in the data. To do that, we have to set up taking the action, the state and the action, pass it through like an MLP, and you get the mean, the parameterized mean, and the standard deviation of the latent variable.
Okay.
And the decoder here takes in the same state that is fed to the encoder, and again latent Z. So here, since the Z is sampled from a normal distribution, it has some noise proportional to the variation, not that variance. So it can output an action that is close to what was fed initially, the encoder. And the goal is to match both A and A tilde. So code-wise,
Quick question. So I noticed you have a register buffer. What's that?
okay. The register buffer is in the algorithm here. We need to take a DKL between the distribution of the latent Z and the prior. So the idea here is that we want to force the distribution of the latent to be close to a normal distribution so that we can sample easily from the later to get what we want. I don't know.
Yeah, that makes sense.
But by constraining it over here, we kind of know where to sample the Z from to have the result we want. And this normal 0, 1, this is what I try to make here. And this is just, I guess, a fancy way of putting a 0 and a 1 into the VAE policy itself, and then obtain the N01 here.
Okay.
Otherwise, every time we compute the AL, little spoiler, but here, once we recover the distribution of the Z and we compute the AL divergence, here, normally, I would have to say like uniform, torch 0 and torch 1, like the output. Correct?
Okay.
But I just, as a shortcut, I just put it into the VAE policy. And that by registering the buffer, it actually helps you move the network to another device. These parameters will also move together, so you don't really need to play with the device again. Later.
Okay. I see.
That's just implementation. Yeah.
I see. Okay.
So to quickly close up with the decoder, well, here it is, takes in the same state and the latent Z, and somehow manage to bring it into, well, outputs a value between -1 and 1, as the actions are usually constrained in that interval. And that's pretty much about it. The internals itself, by that I mean the forward function, well, this is what's happening here. You feed in the state and action, you get to Z. Right? Encoder and get action that should be as the experts. And the loss here, okay, this goes into just a quick mention of the perturbation network here, which the equation is like the normal distribution we sample the noise from in TDPG, for example. We want the actor to look around a bit from what it perceives its optimal distribution over action. But here they parameterize such a network so that because the VAE policy in the end, it will match exactly what the experts, not exactly, but very close. So if the expert is not optimal, intuitively you want to explore around to get maybe even better performance. So I think that motivation behind the perturbation network, which we talked about, right? So that once you have the value function, despite the constraint on the VAE policy, the bias toward the actions of the expert, you can add some noise that will further improve the performance of the overall policy. So VAE plus perturbation becomes a whole policy. I think the objective here should probably give a better intuition. So here is the pi s. So we have the Q function here, or SAC. So this is the action that comes from the VAE policy. Really close to the experts, and then we add some noise. And since the perturbation network is trainable, we can maximize the perturbation network that gives us best performance, even better than the experts. And this is based on the Q function.
I see.
The equation behind it. So it's a simple MLP, not much to say here, just that they constrain the output of the noise with the max perturbation, which is another name for this. So actually, it's a big phi. This is where hyperparameter comes in. Okay? So yes, this is how the noise is done. Here there is the network initialization. VAE policy, interestingly, does not use the target network, only the perturbation network. This one. So declare those, also declare the Q functions. So far, nothing really out of the ordinary. And I guess now we have the updates loop here. We'll sample some batch. And then with the VAE, we did the state and the action of the batch. Reconstructed actions. And the reconstruction loss here, they offer just to use the simple MSC loss.
Okay.
So you can reduce the distance between the expert's action and the VAE policy. And the typical loss here, which is this part here, between the Z and the prior we have defined before. I use the, well, you probably know this one already, the KL Divergence Method, Python. Just give it Z this, and the prior we have in the and this becomes the full loss of the VAE policy. So here I wrote the this is a really small detail, probably no need to go over this one. Let me just do equation first. So far. So far. Okay, so here I think they have a pretty formulation for the loss, which was quite easy to follow. Here we can notice they also use lambda here, and the lambda in the algorithm was defined as the mean Q weight.
Okay.
So this comment here is actually to remind me that in the original implementation they did not use the lambda, just a constant, but I still have to find the reason, I guess. So with this, we can train a VAE that imitates, in a rigorous sense, almost the actions of the expert. And so the next part is to update the Q function using standard Bellman equation updates. With a slight difference here, there is a. Oh, I need to go up again. Sorry for that. Okay, so here they have a special term to update the Bellman equation. So here set the value target y as per equation 13. And equation 13 just here. is a form of trade-off between an overestimating and an underestimating, or in other words, conservative Q function.
Yeah.
So here the
Is this basically the same clip WQ learning that is used for TD3?
Oh, okay, I see. So they even use it there.
Yeah. Like, especially when I see their code, it looks very similar.
Well, they also mentioned it here. So I guess that's it. Is this a paper on its own or something else? Like
This is, I think this is by itself. The double Q learning is by itself a paper, but clip double Q learning seems to be something very specific to the author's paper.
I see. So, if you could please refresh my memory, double Q learning is the one about using target networks, right?
Yeah, I'm having a hard time trying to remember, but I was just going through BCQ's code, and in the clip double Q learning part, it looks very familiar with the TD3 code. So I feel like they might have reused that part of the code.
Yeah, I think they make reference to Fujimoto et al. 2018 on the page that so on page, doesn't have page numbers, and that's good. 6. Well, basically, if you go to equation 13, then just at the top of the paragraph, it says clipped double Q learning, and then it's got a reference to a paper.
Yeah, then it's definitely TD3.
Yeah.
So, but the point of TD3 was probably not the clipping of the double Q learning.
That's one of, so TD3 had I think 3 innovations, and clip double Q learning was like one of them.
But in any case, that's how they compute it, and this is where the lambda term comes into play. So in a sense, it also looks like the lower bound that the SAC CQL sets, just that they do not learn this parameter, for example, which is kept fixed. Okay, so once the Q function update is done, the last part is to update the perturbation network, which will learn to noise the imitated actions of the expert so as to get a little bit more performance. And this is equivalent to the simple update policy in either DDPG or SAC. First, sample the raw action from the VAE policy. And here we do not need any gradients in this part because it's only the perturbation network that will be updated. And then sample the noise for the action, add it to the action, ramp it to make sure it does not exceed the range, and then evaluate the sampled action with respect to the state using the 2Q functions. Take the mean, and the objective becomes to minimize the negative of the Q value, or maximize itself. And here, another, let's say not bad thing is that I use the 2 networks as SAC, but the author recommends only using the first one, or at least only one. So I don't really know the impact exactly yet.
I see.
Or on this algorithm, I will say. Next thing, you have the target network updates. Here, better not forget the perturbation policy. But beside that, the rest is a standard reinforcement learning code boilerplate.
Right.
And with this, I only got a few experiments to run. Let me zoom in. So the idea was to just run a few experiments and compare to the SAC CQL. So here I took as a baseline the SAC CQL from the last development cycle. The black tip placed the data of the experiments, and the other colors were basically BCQ on the medium dataset from D4 era.
Right. Could you zoom in to the first couple, let's say 500 iterations?
500?
Yeah, because it looks like BCQ just learned really quickly in
Yes.
its initial gradient steps, and then it just sort of converge over there. But it looks like, for example, the BCQ didn't even get a single instance of, let's say, 0 reward, which I thought was a little bit curious.
Well, this is probably due to the evaluation process. In any case, before evaluating the agent over here, there is bound to be a few updates already.
Okay, I see.
So that would not be surprising. And it takes at least 1,000 iteration before getting to this.
I see.
But the TCQL, I don't really remember how it's done.
Kind of reminds me of the old saying, yesterday God and I know what I wrote, and today only God knows.
Yes.
Yeah, something like that. But okay.
I also recall that, okay, not a recollection, but the key difference between both networks, both methods, is that BCQ, in the end, is really focused on the action. So it does not really matter what you learn as a policy overall, as long as you can copy the actions of the expert. Well, that's basically what the BCQ losses encourages the agent. But in SAC CQL, it's more about learning a good Q function so that you can use it to learn a policy that extrapolates better. Well, I have a few more comments on that one. So in this medium data set for Hopper, I think that, well, the performance saturates over here 1,000. Comes there really quick, but then you don't really have much improvement. Meanwhile, the SAC CQL actually manages to achieve higher performance than what seems possible with BCQ. And I thought that since the VAE policy, the BCQ, it's basically trying to imitate the T4TAT action of the expert. How about adding some noise, right, using the perturbation network to the imitation process? Because I was not doing this here, I was just doing pure imitation. So once you add the noise sample from the perturbation network, you can actually see that there is a drastic improvement in performance, albeit a little bit noisy.
Right.
And it to match the SAC CQL performance to some extent. This part I did not know. I did not see yet because the runs just finished this morning.
And I think the performance chart that you're showing sort of matches really well with a lot of what is being shown in the paper, where the performance increased to a point, and then however many updates you try to do, it wouldn't really improve its score other than that.
So it's a form of overfitting, I guess.
Maybe not overfitting, but it's more like a bottleneck, maybe, to some extent.
Okay. But I guess it should be important to keep in mind that it's also a medium data set, so it's not really that optimal. And yes?
Yeah, I was just thinking. So remember, the author had a couple settings. The final buffer, concurrent, imitation, imperfect demonstration. So I guess since we're using a fixed data set, are you using the expert data set?
Expert? You mean the D4L expert or
the
final?
Are you using the D4? You're using the D4RL data set, right?
Yes.
Yeah, so that would be sort of the imitation learning performance, right?
I see. So final buffer.
No, not final buffer, but imitation performance. Because final buffer is what you get after training the agents from scratch, and then you get the entire buffer, all of the transitions and stuff. But since if you're using the experts data set, it's more of a imitation learning that you're imitating from the expert, that kind of thing.
I recall that in default error, the data set is ultimately the buffer of the agent. I recall they mentioned in a maybe random, proper random, we put the first 1 million step, no?
Yeah.
It's, so the medium one, which I think is the one that you've used, is an agent, like soft actor critic, trained up to a third of the performance, and then that agent is used to populate a replay buffer. The one where they use the actual replay buffer that's used to train the soft actor critic is called medium replay.
Medium replay. Okay, got it.
Yeah, so medium is kind of the one where you train an agent up to about a third of what they think the best score is, and then they collect data with that agent. And then the expert is the soft actor critic trained all the way up to its best performance, and then using that to collect data.
I see. Thanks for the heads up.
So I've been using them quite a lot. I've become quite familiar with them. And a random is just random actions. I don't think it's any particular policy. It's just complete noise, essentially.
That will be very interesting if an agent can learn from random.
Yeah, and I don't think I've come across one yet. They basically all get to about, so in Hopper they get to about 300, which is basically just random actions. Like they have like maybe up to 350 or 400, but it's not anything exciting. But yeah, if someone comes up with an agent or an algorithm that can learn from random data, I think you've definitely got a publication there.
Yeah. I guess it's something at least. Okay, so there's also the matter of data sets. Roger that.
Yeah, yes. So you've got your different data sets, and then you can basically, you've got your main hyperparameter is phi, isn't it? Your kind of max perturbation.
Yes. Well, yeah. I tried to play with 3 values of perturbation, and at least in this case, it does not seem to make much difference.
So something that you might like to try, which I've only tried on one data set so far, is to so in their code they train the VAE at the same time as the critic and the actor, but you can actually train the VAE prior to see if that helps. So it's just a thought. I've got one experiment, like when you're finished, I can show you that I've got one little experiment that I tried on the medium expert data set, where pre-training it actually made it seem to perform better, although it's got some very strange learning curves.
This kind of, because in the end you will have to pre-train the VAE on maybe, let's say, the full 1 million steps, or maybe half.
Yeah, so I thought about that after I'd done it. So when I did it, I just trained the VAE like they do in their code, which is to just sample from the replay buffer. But if you were doing it properly, you would iterate over the entire data set, I guess, which I haven't done yet. So,
keep it. Do some experiment with the different training schemes on top of the data sets.
By the way, Rosalind, so I was looking at the author's source code, and something that was a little strange to me was the author didn't seem to really have this perturbation network, or rather it just seems to have used its actor as its perturbation network. So if you look at line, what's it called? It's 175. So the author really directly just uses the actor as sort of the perturbation network.
Maybe both are, let's say, yes, the perturbation network. The actor here is probably VAE plus perturbation, I think.
Sorry?
The actor here in the upward code is probably VAE policy plus. Wait.
Oh, I see. So there is an actor defined, but there's also another actor defined under BCQ class, and that might be different.
Okay, I think perturbation network is actor here.
Oh, I see.
I think actually, so it is a bit confusing. So what that actor is, it has the VAE and the perturbation model in it. So if you look closely at what the actor is actually doing, so it's taking in the state and the action, and it's outputting A, which is kind of like the amount to alter the action by. But then what they do is they add A onto the action itself and then clamp it. So it's kind of, so it is the perturbation model, but so the actor is kind of the VAE plus the little perturbation, and then they bring it all together as the output. So they call it the actor.
I see.
That's a bit confusing, but
It is a bit strange. And something that I also noticed is that they seem to have just implemented the KL divergence loss directly, just using the formula. If you look at line 142.
Yeah, I think they've done that because they're both Gaussian, aren't they? There's kind of like a shortcut, if you like.
nerds.
Like a sample-based KL divergence, if it's slightly easier, I think.
Yeah, and also I have a little reservation with respect to the KL divergence implementation given by the Torch package. So I was doing with a little experiment some time ago with phasic policy gradient. Essentially, it uses a large. It has very high GPU memory requirements. So what I was trying to do is to do gradient accumulation instead. That means when I do the back propagation, I don't immediately update the model's parameter, but rather I do another gradient backwards. So in essence, this is a little hard to explain, but maybe I can find like a code sample to explain. But essentially, what I found is that gradient accumulation should be theoretically equivalent as just doing the whole batch. However, if I were to do it with the Torch KL divergence stuff, then the resulting gradient is not the same. So not exactly sure what happened. Was a little confused.
Probably some implementation by Torch distribution KL divergence. But in essence, they are probably doing the same computation, I think.
Yeah, so let me share that part of the code real quick. If you don't mind, Ross, and I'll take over the presentation real quick. So if you look at this two part of the code, this is what the second one is gradient accumulation. The first one is direct backwards propagation, but sometimes the batch could be too large. Therefore, essentially, you just do a lot of backwards, and then after certain gradient accumulation steps, then you step and then you zero out the optimizer. So it's a rather smart way to say, oh, if you have GPU memory issues, then this is something else that you can do to reduce it. But what happens?
It could be really useful, actually. That's good.
Yeah, it's very helpful, and I did a little test with it, basically. Let me see, phasic policy gradient. So look at this source code, right? This is just regular batch pass through, where I just say the real value lost out backward, and I print out the gradient for the actor, and it's about this much. And if I do the gradient accumulation, so I have a certain number of gradient accumulation steps, and I was able to get the same result. But if I do the KL loss using the KL divergence function, then the gradient for the policy is different.
Well, the error does not seem that big, but I guess it can impact the result. Okay.
Yeah, I don't know. It's probably not an issue, but that's just something that got me kind of curious. Not sure if that was the right way to handle it every time. but but yeah, just some sort of off-topic thought.
Yeah, actually, maybe a more exact computation might be desirable, because in PyTorch they probably have to take into account like all the distribution that could be used with the function KL divergence.
Mm-hmm.
So there might be some additional tricks which change the result a little.
Yeah, that could be very, very well be the case. By the way, Rosalind, have you had a chance to try the D4RL dataset directly with the author's source code or something like that?
Not yet.
Okay.
I mean, I've done that just for one little thing, one data set. Yeah.
Okay. I was just wondering, if there would have been a performance difference between Rosalind's implementation and the author's original implementation. So, for example, Rosalind, you were demonstrating the performance in Hopper task. So the dataset is different, right? The authors uses a Hopper v1 dataset, and I presume the dataset in D4RL are Hopper v2. So there could be a difference there. But I did notice the the return for your Hopper v2 is around 1,000. What was it? Yeah, but for the author's implementation, it seems a bit higher. So I was just wondering, maybe there's some tricks that doesn't. Maybe it's a little counterintuitive, but it's actually really important for the performance.
Yes, it's definitely possible. I will try that. Try to edit their implementation and add some run to 1DB so we can have a straight comparison, I guess. Yes. There's actually a really critical thing I seem not to be doing yet, which is let me see. I wanted to mention it at the end, but I guess we might as well do it now. When I sample from the VAE policy, for example, I only just sample one action. But in the paper, they recommend,
sample multiple actions at once.
Yeah. It's like 100 or something.
And you take the best one, that batch for each state. So that's definitely one thing I wanted to work as a next step.
Yeah. I think that sounds good. I think it's usually a pretty good idea to use the author's original implementation to set up a baseline, and then see if our implementation matches the result. Because sometimes when you read the paper, it could be easy to we could miss things. Long story short.
Yeah, it
And
was
also,
rush the jobs.
and also they do, when they actually select their action, they do 100 samples from the VAE, and then use the actor to generate 100 actions, then take the action with the largest critic Q value.
Yeah.
So a little bit of extra bit there as well. So you've got kind of there's 100 actions for selecting the best action, and then in the critic training they duplicate the state 10 times to get 10 Q values. So there's a bit of kind of stuff that's under the hood, if you like, that probably will help a lot when it comes to performance.
I think their agent manages to, I don't really know the specifics of their data set, but it managed to get 3,000 if we refer to the imitation performance to be using.
Mm-hmm.
Probably can do better, definitely.
Yeah, so it looks pretty promising. I'd be quite interested. Another thing is, so I look it up. The BCQ has a discrete variant, which the author suggests, for Atari games, for continuous actions environments, they have to do a lot of tricks. But for discrete action space, it's somewhat more clear as to what to do. So they have a NeurIPS workshop paper that talks about it. The other changes that they have to do to modify it.
Is it different from the DQN? Like they use the DQN, but for continuous tasks in the paper.
I'm pretty sure it's different, right? Yeah, it's different. So if you look at the BCQ repository, let me maybe share my screen. So if you look at their source code, from BCQ's official repository, you see their DQN, the convolutional neural network for the Atari, the output is a number of actions. So they're not really using the continuous discretizing, that kind of stuff. And also, if you just over here, there's actually a README that shows, this is a discrete batch constraint Q-learning. And then if you open this, the DeepRL workshop NeurIPS paper, this is where they go into the details of BCQ. Yeah, so over here they have discrete batch constraint deep Q-learning. So myself, I would be quite interested to try to reproduce it, see if I can draw a comparison with CQL.
So that's for the discrete case, discrete tasks like Atari.
Yes. So they have to do things a little bit differently, but the authors say it's supposed to be easier, more intuitive. So the authors say much of the complexity of the original algorithm is introduced to deal with the continuous action space, and the core principle of the algorithm can be maintained in a much simpler manner in a discrete setting.
Yes, because in continuous you do not have a finite distribution over all the actions, so you have to kind of sample, do Monte Carlo estimates.
Right. Yeah. So for the offline benchmark, so what I hope to do is I guess instead of running a lot of benchmarks, what I think might make sense, at least for the discrete case, is to just simply focus on one setting, like on breakout, and then use the expert data sets instead of running on a lot of Atari games and then using. It's sometimes a little more challenging to keep track of things, I guess.
Indeed.
And
maybe once we do all the experiments for one setting, then we can maybe scale it.
Yeah, exactly. I think those would be a good point to do that. And by the way, if you look at this is a surprise finding actually the other day. So if you see the performance of offline DQ and CQL, it actually performs really well in QBERT. That it almost matches a lot of the existing algorithms, really.
Well, it's still based on expert data after all. Or what kind of data set? Is it expert?
Yeah, it's expert.
Well, not surprising either.
Yeah, but it's surprising in the sense that compared to other environments, CQL usually doesn't perform that well. So for example, over here, it's able to, it couldn't even match DQN, right? Yeah. Anyway, just some thoughts about maybe how are we going to go around this issue.
Interesting. Let's keep that in mind.
Okay, sounds good. So I don't have any updates. So I guess for the next week, let's just keep working on it. I'll start working on the Atari case. sorry, this week was kind of busy with some other stuff, but next week, hopefully I'll get some time to try to work on Atari stuff with BCQ. Yeah, other than that, yeah, Alex, what are you going?
I was just going to say, so if I just quickly share my screen, I'm going to I'm going to try looking at training the what would I know? Training the VAE. Pre-training the VAE. So can you see my screen now?
Yes.
Yes.
So this, I think I may have messed up the code a little bit here, but this is the Hopper Medium Expert while training the VAE at the same time. So it kind of does all right, but really want it to be close to 3,000, 3,500. So then I tried pre-training it, and I got this. So it actually was on par, but then it started doing quite well, and it stayed there, which was quite nice. Like if I get rid of this, you can see it's actually relatively stable. And I thought, I wondered if that was a fluke, because sometimes it happens. So I tried it 5 times with 5 different random seeds, and I got these results. So there's another one, which did even better, but had a bit of a wobble. There's another one, again, a bit of a strange learning curve, but it kind of all ends up in the same place.
Nice.
And then I did it another 2 times because I still didn't believe it, and then I was starting to believe it a bit more. So I think training it prior to the actor and the critic may have some benefits, but then it might only be for this one data set. So I'm going to try it on some of the other ones, and I'm going to try it on the medium and the medium replay to see if it makes any difference for those.
Quick question. So for these, when you say pre-train, do you mean before training the critics and actors, you just sort of train the VAE just on the VAE for a fixed number of steps?
Yes. So essentially, they've got their code, haven't they? Blah, blah, blah. So they have, in their bit where they train the BCQ object, they have this part here, which is training the variational autoencoder. Basically, take that out and do it on its own, and then just do, which is what I've done now.
Okay.
And then, because really, you can do them completely independently, really. So you do that, and then once you've done all that, then you do this. What I didn't do is train the VAE on the entire data set. I just trained it on random samples, like you would do if you were training all of it. But I don't know if that means it would take a long time to train the VAE or not. So if you look at the loss for the VAE, it does go down quite quickly. So this is the VAE loss when you pre-train it. It goes down quite quickly. So that's over 500,000 iterations. But if you did it over the entire data set, you might not need to do it as much. So it's just, I'm going to experiment with to see if it makes any difference.
I see. That makes a lot of sense.
Question.
Yeah.
Once you have pre-trained the VAE, you still continue to train it along with the policy?
I didn't, but you could do, I suppose, if you wanted to. I mean, I don't know if it kind of looks like it's bottoming out a little bit in terms of its loss. So there might not be much need, but you could try and see if it makes any difference.
Maybe the intuition is that if the VAE is jointly trained with the other components, the change in the latent phase will kind of confuse the perturbation network, and the latter could not thus find a consistent noise policy to achieve high results, maybe. But again,
so I mean, I only did this once, which is training it at the same time, and that could just have been a bad run. It could be that this is just, actually it keeps going up and up.
But you also use the action repeats, right?
Yeah, so I basically just do very similar to what's in their code, but train the VAE. I got that idea from the the PLAS paper, because they pre-train the VAE, and then their main difference to their paper and this one is they don't have a perturbation model as such. Well, they do, but that's in addition to another model. They actually train the actor in the latent space rather than training it afterwards. So that's when you end up with some promising results like this. I thought it was quite nice. It kind of learned almost straight away, which was really weird. But I think that was a fluke because I only ran it the once.
I see. Also, a quick question. Did you include the videos of the agents playing the game by any chance?
I haven't got these yet, no.
Gotcha,
Not yet.
gotcha.
I'm going to make it into a nice little kind of report thing. But I've just got the scores at the minute.
Gotcha.
No, I think I did one report, but that was for PLAS. Let me just see. Where's the reports?
Nice. Oh wow.
Yes.
Oh, there you go.
Here it goes.
Nice. I always like to see the agents, on the other hand, just trying to do his own things.
And I think I did half cheater as well. He just runs off and just keeps going forever.
Oh wow, that's really nice performance. Yeah. This is with PLAS?
Yeah. This is with PLAS with a very slight. So this MA is the max latent action. So if it's 0, it's basically the same as the data, and you start to get actions that are different to the data set. And this was the best one I found, so I made a video of that one.
I see. That's really awesome.
Yeah, sorry. That's a bit of a tangent, but yeah, I'll try and do some videos for the actual what are we on BCQ.
Yeah, that sounds good.
I'll just stop for something. Has anyone, just out of interest, looked at any model-based stuff yet for reinforcement learning?
I haven't looked much into it. The only thing that looks pretty interesting to me was not the only thing, but something that really stood out to me was Mu0. I really want to look into it, but I haven't had a chance.
Yeah, does that use Monte Carlo tree search and all that jazz?
I think so. Yeah.
Yeah. It's my supervisors asking me to look into model-based stuff, and then naturally that will lead on to offline model-based stuff. And I just wondered if there was any, apart from something like Dynet. I don't know if you come across that. I've not. They all seem quite complicated. They kind of seem intuitively quite simple. Sort of learn a model of the transitions and the rewards, but I seem to be having problems when it comes to things like terminal states. My model doesn't seem to know when to stop. It would just, if I try to train an agent on a model, there's no done criteria as such. It will just keep going on and on and on and on and never actually reach a terminal state.
I see. I feel like the model-based RLs are still mostly in development, and you see new ideas every day. Mu0 is like the only one that seems to be quite battle-tested across domains. Yeah, so anyway, that was, yeah.
Does that only work on when you already have a model, like in like games and stuff, or does it learn a model?
It learns a model.
Ah, cool. Okay. Nice.
Yeah, it's pretty cool. Because I was thinking about other model-based RL methods. They're usually, more complicated, hard to reproduce, and usually I feel like if you reproduce it, and at that point there's much better model-based methods that are being proclaimed, and maybe after a while, it just feels like you could get outdated very, very fast.
Yeah.
So yeah, that's why I'm being a little bit hesitated to try out these model-based methods.
Yeah. Okay. Interesting.
But yeah, they certainly could be quite interesting to try it out.
I thought they would be quite good for offline because you've already got in some cases, like in the default RL, you've already got such a big data set that I feel like you should be able to create a model with it, but it just doesn't seem to work. In a kind of really naive way, it doesn't seem to be working very well. But anyway, that's basically what I've been trying this week, and hadn't really got very far.
Yeah, for sure.
Cool.
Cool. Does anyone have any thoughts or comments?
No. No, but it was all good to see things here. Thanks for sharing.
Yeah. Thank you for participating, guys.
Thank you.
If there's no any more questions, let's try to wrap it up. So next week we'll keep talking about this, and hope you guys have a good weekend, and talk to you next week then.
Thanks, everyone.
Yeah.
Cheers.
Thanks, guys.
Thanks, everyone.
Yeah. Have a nice weekend. Bye-bye.
Bye.
See you. Bye.
Bye-bye.
Goodbye.